you. Our next the first talk is a distinguished keynote from Professor Viktor Prasanna from USC. The topic is FPGA accelerators in data center. So thank you, Professor, for giving this talk. Thank you. Go ahead.
I hope you can see my screen and also hear me.
Yeah. Pretty good.
All right, thank you very much. I'm very pleased to be here to offer this keynote presentation today to the audience, and then hopefully interact with the audience as well as I give this presentation. My talk today is focused on use of accelerators, FPGA accelerators in the data centers. This is a research we've been conducting over many years in using FPGAs and acceleration by using FPGAs. And this talk will look at what happens when we use FPGAs in data centers, and also illustrate some examples of the acceleration that we can obtain by using this accelerators, FPGA accelerators. You can see many of the publications at my website. I welcome you to visit the website. Looking at the FPGA lab and the data science lab, I have listed those URLs here, and you will find many of our publications that is related to this presentation today. Please ask me questions if you have as we go along. Also, I think we can use the chat screen also to ask me questions towards the end as well. So this talk I've organized this to look at how the technologies evolved in the space of FPGAs and how FPGAs are being used in the cloud. That's kind of the initial portion to give you the background here in terms of technologies and FPGAs in the cloud and in data centers. Following that, I will go through a specific technology that we have developed over the years in terms of how to design these accelerators, very rigorous mathematical approach using the design space exploration. I will go through that in detail to illustrate using some examples. What happens if you use this kind of a methodology and use FPGA accelerators, what kind of performance improvements we can get. Following that, I will kind of get into some discussion about what are the future opportunities here, what kind of challenges we face in this community in terms of being able to use these accelerators to effectively make use of these accelerators from an application perspective. There is a later portion of the talk that will discuss these ideas in detail. I probably will not be able to go through all the examples I've listed here. I will cover at least 2 of these examples, so you get a sense of the kind of opportunities we have in being able to use this technology to get high performance parallelized implementations for various applications and kernels in diverse application spaces. So first of all, the context here for this research, for this presentation, is that we have large amount of data coming to us today. We have large number of sensors. For example, your own cell phones are sensors. Quite a bit of data is accumulated, processed in real time in these kinds of sensors. So this data is everywhere. We perform various analytics in the loop. For example, you may do a machine learning inference in the loop to identify what kind of objects, where the focus of attention is going to be. All these computations is distributed. Number of times or real-time constraints have to be satisfied here in these kinds of applications. So in principle, computation is occurring everywhere, and you collect the data, and then this computation in many of these cases occurs in data centers, where you send this data to the data centers, and then the data centers performs the acceleration for you and gets back the result to you in real time. So in the big picture, many of these applications are going from traditional computing workloads to data science workloads, where we do various types of machine learning kind of applications, artificial intelligence applications, and these applications need to be performed in real time. So if you look at the computing landscape, so the data is collected at the edge. I've shown various examples here, various examples where large amount of real-time data is collected. And typically, this data is sent to the data centers using internet backbone, where the actual computations take place. So what happens in this context is that accelerating these computations using traditional processors perhaps may be challenging. That is a context under which accelerators become important in the data centers for these kinds of applications. And today's talk and discussion illustration is focused on how can we accelerate computations in the data centers by using technologies such as FPGAs. I will focus on FPGAs in particular and also compare what kind of performance improvements we can get by using FPGAs compared to, for example, GPUs and multi-core platforms. So our context for today is the acceleration in the data centers using field programmable gate arrays as an enabling technology, and what are the issues in mapping applications, what are the opportunities that we find here in this space, and what are the directions we can explore here in terms of enabling this technology, using this technology to be able to perform all these kinds of data analytics in the data center. I will also comment on use of some of these technologies, FPGA technologies in edge computing, but the main focus will be if you have cloud platforms available and then we are using FPGAs in that context, what kind of acceleration, what kind of performance improvements we can obtain. I'll illustrate these ideas by looking at two specific examples, graph analytics and also privacy preserving computations, which are very important computations, which are computationally demanding, and then demonstrate how FPGA technologies can be used here to get high performance. Just to get some introduction to the kind of technologies that is going into the data centers, into the cloud platforms, I'm showing here the technology evolution in terms of computing fabrics. We have CPUs, GPUs, FPGAs, that's the focus for today. And then also looking at compute fabrics, which are accelerators, for example. I'm just showing here one of the application-specific accelerators. The graphics here is one of the largest accelerators in the market, the Cerebras wafer scale CS2 system. In the middle portion here is a various interconnect technologies. A lot of new technologies have already been integrated into the data centers, into the cloud platforms, where we can connect various devices, including various memory technologies, and evolve them into highly optimized accelerator enhanced data centers. That is where our opportunities exist for being able to accelerate these computations. Just to make sure that we are all on the same page with respect to this particular technology, I will be covering in detail FPGAs. I'm showing here the block diagram of how an FPGA looks like. The basic building block here is the logic cells, which are essentially programmable. That means you can program any of those 4-bit functions, for example, by programming the 2 to the power 4, 16 locations inside the logic cell. That is what is called a lookup table in technology terms. There is also a programmable interconnect, horizontal lines. You have X and Y axis lines here, which are used for interconnecting these lookup tables to complete complex functions we can implement on these devices. Finally, we also have programmable on-chip memory. There is quite a bit of static RAM available on these devices, typically organized into blocks. And then you can do extremely high performance, very high bandwidth computations by effectively using these lookup tables, the interconnections, as well as the static on-chip memory on these devices. I've shown here that as FPGA technology has evolved over the years, we get these devices in the market which are very powerful, in some sense comparable in performance to the high-end CPUs as well as GPUs in the market. These devices consist of this programmable logic, interconnects, memory, as well as hard IP cores. For example, you can perform floating point operations on these devices. You also have quite a bit of a memory hierarchy, static memory hierarchy on these devices, including you also have high bandwidth memory that is integrated onto these devices. They also come with quite a bit of external memory interfaces, for example, Ethernet interfaces, PCI interfaces, DDR, DRAM interfaces. All these provide extremely high bandwidth to the external devices that you might want to interface to these accelerators. I'm just showing here example devices in the market. I'm showing, for example, here the Xilinx Vitis series of devices, state-of-the-art devices, technologies used in these devices here. Very large number of logic cells, lookup tables I talked about earlier, in the range of 10 million logic cells are available on these devices. Very high performance for integer arithmetic, 38 teraops that you can do for integer 8 arithmetic on these kinds of computations. Very high bandwidth external devices, including a high bandwidth memory available on this. Plus, you also get various external interfaces, including PCI Express interfaces available for these devices. You also have a number of other vendors that provide it. For example, Intel also provides very high performance devices. I've just given an example here. These have extremely high performance in terms of the bandwidth, in terms of the number of lookup tables, in terms of the on-chip resources available for us to map to accelerate various data analytics computations on these devices. As the technology is evolving, there are a number of interconnect technologies that have become very popular. In fact, there is a consortium that is looking in the context of data centers and cloud platforms to be able to interface these kinds of FPGA devices into the processors, into the node infrastructure in these devices. This is an example of interconnect technology. By doing this kind of a technology, this will work on top of the PCI Express interconnect, hardware interconnect, and then you can get coherent access to the DRAM of the processor you have in the system, meaning that you don't have to copy the data. You can share the data between the FPGA and the processor and then get extremely low latency, high performance implementations by exploiting this technology. Just to give a sense of where this technology has progressed over the years, this is an example of the software technologies available. So you can go in the market today. This particular technology currently is marketed by AMD, where you can get these various libraries available for our interfaces so that we can effectively use the FPGAs in that context. We have various compilers, various high-level programming frameworks. For example, you can directly go from TensorFlow into FPGA accelerator implementations, which makes it very attractive for end users to be effectively able to use these technologies without getting into the low-level hardware details of the FPGAs. Just under the hood, if you're trying to program these devices from a hardware perspective, there are quite a lot of tools available. Also, the level of abstraction has been raised in these kinds of programmable devices. So today you can program these devices by using high-level synthesis. You can write a piece of code that looks like an OpenMP program that you might write for a scientific computing or a parallel computing application. And then you can directly compile that, execute that on the FPGA devices. This is just an example here, the kind of features available so that you as an end user can specify what kind of accelerations you want to do. For example, you can specify loop parallelism inside that. You can specify pipelining. You can specify what kind of data partitioning you want to do so that we can effectively use the on-chip, the block RAMs I talked about earlier. So there are a number of such features are available at the high level so that the software developers, application developers can directly work with these devices without getting into the lower level details. It makes it very attractive for end users to be able to program these devices by using these technologies in which you have control over the hardware. You can specify what kind of a caching mechanism that you would like to use, what kind of pipelines you want to build, how many memory controllers you would like to have, how do you want to handle data dependencies in the computations. So you have this full control over the hardware. So you can go to the lower level programming if you wish, or you can stay at the higher level, use the high-level synthesis features, and actually compile the complete hardware to perform your acceleration. I'm just showing you an example of a kernel design, a classic example from machine learning applications where you have to perform dense algebra problems. You can synthesize these systolic arrays by using high-level synthesis tools. Just an example I'm giving here in terms of the amount of time that you will spend to be able to perform this synthesis using high-level synthesis tools compared with what happens if you were to use RTL or register transfer language or Verilog kind of implementations. I'm also showing on the right-hand side is that this high-level synthesis tools produce very good results these days, even though they are not optimal, but they're reasonably good results. You can do this very, very quickly. On the lower portion here, I'm showing the kind of performance improvements we can get for typical operations by exploiting the systolic array kind of implementations compared with what happens on the CPU. Significant performance improvements are possible by using this high-level synthesis and performing this mapping onto these devices. Just to summarize this line of technology evolution discussion today, I'm showing here various FPGA technologies And then what is the comparing them with the multicore and GPUs, also comparing with one of the largest accelerators in the market, Cerebrus wafer scale integration on the rightmost column. I'm comparing with respect to various features row by row here, but I will not go into the details. Just for us, for example, these FPGA devices consume lot less power compared to what happens on CPUs and GPUs, typically about 1/4 or 1/6 of the peak power compared with what happens on the processors as well as on the GPUs. With respect to the number of transistors and technologies, these are state of the art. They're really using leading edge technologies for implement them, extremely high package and packaging technologies, interconnect technologies that are used here, which gives extremely high densities in those implementations in the range of tens of billions of transistors that are used here to get extremely high performance in these implementations. I've also shown here in the last row of this, in terms of the peak performance we can get on these devices. For example, if you look at some of the FPGA devices, you can get 100 plus teraops for integer arithmetic on these devices for various data science and machine learning applications. So these are extremely high performance devices. Plus, you have the complete control over the hardware. If you can effectively use the hardware, do hardware software co-design on this, you can get very high performance on these implementations. Just summarizing here, FPGAs in the cloud in data centers, what happens, kind of the scenario here, these kinds of FPGA cloud architectures are currently in practice. Various vendors provide these kinds of accelerated cloud computing where you have processors, large amount of DRAM, you have quite a bit of accelerator interface to that, including GPUs, FPGAs, and other accelerators. On the right-hand side here, I'm showing here in the table in terms of the typical performance that you can get with respect to the interconnect, that when you interconnect these devices into the node architecture you have in terms of the node-to-node connectivity, as well as between the processor and as well as the FPGAs you have in the system. Within each node, there's quite a bit of technologies I mentioned earlier in terms of interconnections. You can get extremely high performance inside the nodes. As we go between the nodes, across the nodes, the performance depends on how kind of partitioning, what kind of mapping you do here, which some examples we'll go through today to understand the performance implications and kind of the speedups we can get by using these kinds of heterogeneous data centers and cloud platforms. So just some examples here. There are various vendors that provide FPGAs in the cloud. And just an example here, if you look at the Microsoft Azure platform, the Microsoft project Brainwave, for example, uses a large number of FPGAs as part of the network interface card, the SmartNIC here. You can, for example, configure a very large array of FPGAs that can interconnect, that can communicate using the cloud resources, the data center resources, and kind of create a very large parallel array of FPGAs that you can map your applications onto. There is a significant amount of work here at Microsoft in terms of designing applications, accelerating applications by using FPGAs. I've just given some example of software that's available, specific operating system enhancements to be able to use these kinds of devices through SmartNIC. Also, there is quite a bit of technology that has evolved so that you can get extremely high performance, low latency, and high bandwidth interconnection among the FPGAs so that you can get high performance implementations. Another example platform in the market is the Amazon platform, Amazon AWS F1 instances, where FPGAs are also available as part of this cloud offering, where you can lease or perform your operations by kind of effectively mapping your applications onto these devices. I've just given some examples here. If you want large instances, approximately in the range of few dollars per hour, that you can take your applications, compile them, test them, and then also use it for production runs on these devices where FPGAs are available as part of the data centers. So moving along, so this kind of the background of where this technology is evolved into the data centers today. So these kinds of devices are available. There are a number of research projects as well as commercial vendors who offer these services where you can take your applications and then kind of map them onto these devices in similar spirit to what you may be doing on the GPUs, for example, to accelerate. Even though FPGAs you perform hardware software co-design. Given that there's quite a bit of advances in software technologies in terms of the libraries available on these devices, high-level synthesis tools, there is quite a bit of activity that the software programmers can make use of these devices so that you can accelerate your computations on these kinds of cloud FPGA-enabled cloud platforms. So what I would like to spend some time on is suppose these kinds of devices, these technologies available in the data centers, what kind of acceleration we can expect to get by using these FPGA technologies in the data centers. So I'm showing here a particular methodology that we have been employing in my research to be able to get high performance in these implementations, to be able to see how we can effectively get high performance in these implementations by using this kind of a hardware software co-design. So what I'm showing here is the layered approach. So what we do in my research is that we model these devices. Modeling these devices means that we provide computational models that look at the fine-grained computations you can do on these devices, or the kind of pipelining you can do, looking at the external memory costs involved, for example, the latency and effective bandwidth we can get. In principle, we can do the computation and communication modeling of this so that we can use this model to derive our applications acceleration by mapping the applications. That is the 3 layers I'm showing here. So we model them and then use that information in the algorithm design, and then perform the mapping by using the software tools I discussed earlier. And this is kind of a hardware software co-design loop that we perform here, so that by doing this process, by modeling, designing, and mapping, and then reiterating this, we can get extremely high performance implementations on these devices. So the general methodology we have chosen here in my research is looking at this from an algorithmic principle by developing these models, computation models, and using those models to drive our algorithm design, the parallel algorithm design, mapping, and the hardware software co-design that goes there to be able to get high performance accelerators, FPGA-based accelerators. So in the next few tens of minutes, I'm going to spend some time to go through, actually concretely go through a couple of examples showing what kind of performance we can get by using these accelerators. The graph analytics is a very important problem area. There is a lot of research in this space. We have been working in this space over many years, funded through NSF and various DARPA programs. In that context, we have developed various accelerators, and I'm going to illustrate here how FPGAs could be effectively used in solving these kinds of complex, irregular problems by using FPGA acceleration for graph analytics applications. So graph analytics, as I mentioned, is an important topic area, research area at this time. There is several ongoing research projects. There is also software tools available on the data centers, for example, to accelerate graph analytics computations. There's also quite a bit of new startup companies that are looking at how to accelerate graph analytics for large-scale graph processing, large-scale applications development and acceleration. The basic idea is that you use the graph structure to represent the various interactions among the entities you have in a particular data set you have. For example, you can take your traditional databases and represent them as graph databases. In fact, there's quite a bit of research in the context of graph databases, and then how do we use graph databases to understand or solve various problems, commercial problems, by using graph structured querying to be on those databases. So typically, the classic problems here are, for example, centrality issues in a social network, or computing distances, or understanding connectivity in a graph. These are some of the classic problems, classic kernels that you solve here. More recently, there's quite a bit of interest in graph machine learning. We have looked at these problems. We continue to work in this space of how to accelerate, for example, graph neural networks. So if time permits, I will go through that as well. So these are some of the classic problems, which are irregular problems, which work on very large data sets that could be speeded up by using FPGA implementations. There is also one important area of research here, what are called streaming graph problems, in which your data set is streaming through the system, and then you would like to explore, understand the data set, and then understand some properties of the particular data stream, the graph representation that you have for the data stream. For example, you might want to know, as the data is flowing through the system, what kind of connectivity information is there. Number of these techniques are randomized techniques people have developed, and a lot of opportunity here for us to effectively use the FPGA resources to get high performance implementations. As I mentioned earlier, these graph databases or ideas are used in many disciplines today. Graph structured data is used to understand complexity of various problems, including in bio, for example, the World Wide Web, or citation network, or in the context of the traffic networks. And the key problem here is that these data sets are very large. They don't fit on the on-chip resources. So we have to carefully plan the external memory data layout, data access, data partitioning, and also the data movement across the various nodes you have in a data center, so that you can get high performance while you use FPGA accelerators in the individual nodes of these data centers. So for the graph analytics, we have been looking at developing a complete framework in which you specify the graph problems at a high level, and then you automatically generate these accelerators for data centers. So one particular technique that is used in graph analytics is what is called the edge-centric computing paradigm, in which you take the edges in the graph representation and propagate the information along the edges. That means you go along, take the information from the source vertex of the edge, scatter it by using the edge information, and then that information is sent to the destination vertex, and the destination vertex collects all the information and updates that. This is a particular paradigm called scatter-gather, and this particular paradigm can be used to solve a large class of problems. Large class of graph analytics problems can be represented by using the scatter-gather paradigm, and that's what we use here, so that by taking this representation using scatter and gather, we can directly map them onto the FPGAs. So what we are developing in this research is complete framework in which you can specify your applications graph analytics by using scatter and gather as the basic building blocks, and then specify various applications. And from there, we develop the memory controller, the processing elements, the interconnections between the processing elements, and then attaching this FPGA accelerator to the overall node architecture will produce a high performance implementation for us. So the big picture here is that we specify the graph analytics by using this computing paradigm, scatter and gather, and then we take the target platform metadata, that is in this context FPGA resources, and then we have specific design parameters. For example, throughput maximization may be important, or reducing the latency is important. Those are the design parameters given to us. Based on that, the tool that we have developed automatically generates highly optimized code for execution on FPGAs, and that is directly mapped to the various nodes you have in the data center. So the critical problems here in this space, I'll just go through a few challenges and the kind of technologies that can be used here, so that we can get very high performance FPGA implementations for it. Graph partitioning becomes very important. In this context, we need to partition the graph and put them on, and also make sure the data layout, so that it ensures very high memory access performance. Memory access, I'm referring to here the sustained bandwidth you have to the external memory here. So the challenging problem here is to make sure that whatever graph you're partitioning, that can be partitioned across the nodes, plus whatever is inside a particular node, that data is partitioned and mapped onto the static memory or the on-chip resources on these FPGA devices you have. So the particular scatter-gather paradigm that we are using offers some nice parallelism inside that. We can perform the scatter and gather operations in parallel, for example, by using the bulk synchronous parallel model of computation. So we can partition that. You can operate on these partitions of the graph in parallel. Within the graph, we have a large number of vertices. You can take a subset of the data and put that on the FPGA resources on chip static RAM and perform these operations in parallel, which gives you extremely high performance implementations. So this is a context under which we proposed a particular methodology, what's called graph processing over partitions, GPOP. By using this methodology, we can partition the graph, work the graph across the various nodes you have in a data center, and inside each partition, inside each data center node, we can work in parallel by using the various FPGA resources. And then we have this two-level hierarchical parallelism that gives very high performance in these implementations. Just to get some details of the kind of challenges you face from an algorithmic perspective, from the innovation point of view. So if you do the straightforward way of mapping this, we have very large number of write accesses to the external memory, irregular memory accesses come into picture. What you can show is that the number of write accesses in the worst case is proportional to the number of edges, which is in the tens of hundreds of billions in a typical large-scale graph analytics problem. So we need to reduce that. So we have developed various optimizations in this context. An example optimization is to particular way to sort all these vertices in adjacency list of this representation you have. And the good news here is that you can perform all this sorting very, very quickly. And typically these adjacency lists are quite small. The graph is very sparse, the degree distribution, most of the vertices have degree less than 20 in typical applications. So given this factor, you can sort all these lists very, very quickly. This is not a time-consuming operation. By doing so, the important result here is that we can reduce the number of random memory accesses, memory write operations you do, including what happens in the local memory as well as to the remote memories we have, which is very important. In the process of accessing these remote memories, we can make sure in our accelerator that the data is compacted into specific bins, we call them, so that we can directly map these bins, write these bins as one operation into the external memory or to the remote memory. That ensures that we reduce the overheads in this memory access, which gives extremely high performance implementations. So the big picture here is that when you have a data center scale system in which you have multiple nodes connected by some kind of a networking technology, for example, software-defined networking, then you have individual nodes in our mapping application that we're looking at here. We have various accelerators, FPGA accelerators. They all perform in parallel by using our GPOP methodology. They locally compute, combine the data, and then do remote memory accesses. By implementing our scatter gather model on the FPGA, you can get extremely high performance. I encourage you to look at this publication in the ACM Transactions on Parallel Computing, which goes into the details of how do we do this partitioning, what kind of algorithms we can develop, goes through illustrations in the big picture of how this partitioning can be performed in the context of data center acceleration. Let me just go through some examples to illustrate the performance improvements we can get. This is just an example of for the graph analytics case here, typical FPGA device in the market. We are using a state-of-the-art FPGA device here. And then the bandwidth is not very high. This is 77 gigabytes per second compared to what you can get on high-end processors as well as GPUs in the market today. We've implemented various graph analytics algorithms. I've just given some examples here: sparse matrix vector multiplication, page rank, single source shortest path, or weakly connected components, classic problems in graph analytics. And what we can show here is that by using our optimizations, I gave one example optimization. We have developed this framework. We can automatically map these applications onto the accelerators, and you can get very good speedups up to 20x is possible by compared with the baseline optimized the CPU and GPU implementations libraries for these classic problems in graph analytics. This particular result is also available in the ACM transaction, in the IEEE transactions on parallel and distributed systems. If any of you are interested, you can look over this publication or contact me offline if there is something specific here that is of interest to you. So let me move along. I would like to go through one more example, which is very important today in the context of data center applications, where privacy preserving computations are very important, in which you collect data at the edge of the internet, and you do not want to send the data as it is, the raw data. There are concerns with respect to security. There are concerns with respect to privacy. That is a context under which acceleration becomes very important, whether it is at the edge device as well as in the data center. That is a context under which this homomorphic and encrypted computations are becoming very popular in the data center scale to effectively kind of address the challenges of privacy and security in these computations. So I want to go through here, show some illustrate here the kind of speedups we can get by using FPGAs in performing this privacy preserving and secure computations by using the fully homomorphic encrypted FHE computations, as they are called, by using FPGAs in the acceleration. The key idea here is that the user, for example, in this case, you could be collecting data on your cell phone, and then you would like to perform this acceleration of the computations on the cloud platform in a remote data center. And you are concerned about the security of the computations and also the privacy, that you do not want to share the raw data. That's where this encoded computations come into picture. One of the techniques that is kind of proposed, that is becoming popular, is the homomorphic encryption, in which you can encrypt the data as a user, and you keep the encryption key with you, and then the encrypted data is sent to the remote server, for example, a data center, and then you perform the computations on the encrypted data. That means at the server, you're not decrypting, you perform in that encrypted space and send the results back in the encrypted space. Then the user will be able to decrypt and get the result. That means you do the encryption, and the cloud platform, the data center, will not know the data. It is just all the computations are going to be performed on this encrypted data, which offers security and privacy in the overall computations you want to perform. The basic computational step here, the idea here from a computational perspective, is that this homomorphic and encrypted computations perform on polynomials, very large polynomials, typically in the range of 2 to the power 15 number of coefficients you have, and these coefficients are typically 32 or 64-bit integers. So the plain text, that is what the raw data you have, it converted into the ciphertext by using this encoding, and this encoded data representation is by using these polynomials with 32 or 64-bit coefficients. And then in this context, we are just giving an example here how FPGAs could be used. The particular threat model we are considering here is that we have the inputs and outputs are private, encrypted, and then the model is kept on the server, and you want to do inferencing on the model. And then this is the compressed model. That means we are doing sparse CNN inference here by using encrypted data at the server to be able to do this inferencing without converting the data back to the raw data to the plain text. And that is the focus of this homomorphic encrypted sparse CNN inference, the batch inference problem here. So in this case, the input images are packed into this polynomials by encryption, and that encrypted data is sent to the server, where you perform the computations and send the results back. So one of the challenges in these kinds of encrypted computations is the amount of data volume, amount of bandwidth you need to access the data. But in the process of encryption, you increase the data size. I'm just showing here the amount of the data transfer that needs to be performed if you perform computations on encrypted data. For a typical CNN inference problem here, I'm showing the various layers and the kind of encrypted data versus the unencrypted data here, the significant amount of extra bandwidth, extra storage that comes into picture in the context of this homomorphic encrypted computations. So the key problem here in the context of acceleration is we need to reduce the amount of data movement we do, so that I effectively use the bandwidth between the server and the processor or the accelerator, and also to make sure that we can speed up the computations on the data center here. So the challenges here, large amount of data to be processed because of this encryption. These data access patterns are irregular. Plus, we also have high complexity, high computation complexity. We are doing polynomial arithmetic on these extremely large polynomials, up to 2 to the power 15 number of coefficients comes into picture. So clearly here, FPGAs can play a big role in terms of being able to configure, providing large amount of on-chip resources in terms of the block RAMs, the static RAMs you have on these devices, plus the extremely high bandwidth available to us on the chip, on the FPGA, which makes it very attractive for accelerating these kinds of computations. So we have performed the data flow optimizations here because the data flow is a critical problem here. I'm showing here on the lower left-hand side for 2 different classic CNN models for the various layers in that. what is the amount of data transfer reduction we can do by reorganizing the computations that you perform on these polynomials, by exploiting the property of the computations you perform in the CNN inference, and that gives rise to a significant reduction in the amount of data that you need to transfer between the external memory and the accelerator. Up to a factor of 4x is possible compared to state-of-the-art, straightforward implementations of this polynomial operations you do in the encrypted computations. So what I'm showing here is the overall architecture. We have a large number of polynomial buffers, interconnection between that and the processing elements. Everything is customized. We specify this by using the high-level synthesis, and then so we can access this data in parallel, perform these operations, and effectively use the on-chip bandwidth on these devices, which is extremely high bandwidth is available on these devices to get very high performance. Just an illustration of the kind of problems, challenges that you face here in this. If you design architecture with a large number of pipeline units, large number of on-chip static memory with the interconnection network between them, quite a bit of buffer access conflicts come into picture because of the irregular accesses, because of the large number of processing elements and the data distribution that you're performing here. So what is important here is to schedule this buffer accesses so that the effective bandwidth is very high. So we solve this problem by using nice representations by using a bipartite graph matching problem. This is an offline problem given a sparse CNN model, given a representation in this homomorphic encoded space. So we represent these computations by using a bipartite graph representation, and then we use for maximal weighted matching here so that I increase the number of concurrent memory accesses in every cycle. I reduce the number of cycles I need to access that. In every cycle, I maximize it by using maximum bipartite matching that ensures that all the processing pipelines are going to be busy doing useful work that reduces the computation time and maximizes the bandwidth to the on-chip resources you have. This is an interesting way to schedule. These results are available in the publications that I'll point out from my website, for example. And then this gives you extremely high performance in terms of being able to use the on-chip resources on the FPGAs to get very high performance implementations. I'm just going to show here some performance results comparing against the baseline implementations. In fact, there is a standard Microsoft library, what's called the SEAL library, which is implemented in OpenMP on CPUs. I'll show here the performance improvements we can get compared with the state-of-the-art CPU and GPU implementations. So what I'm showing here on the right-hand side is for two classic models, CNN6 and CNN11, 6-layer and 7-layer models here. I'm comparing here, the baseline here is the uncompressed model running on the CPU. And then what happens if you compress the model, that is the sparse CNN implementation on the CPU. And then I'm comparing that with respect to what happens if you were to do the FPGA. And I talked about two different optimizations, data flow optimization and the scheduling optimization. I've shown here the impact of these optimizations overall. So in summary here, we can get up to 10x end-to-end speed up compared with the CPU baseline, the dense CPU baseline, and up to approximately 5x improvement compared with the sparse implementations on the CPU. We can also get significant performance improvements compared to GPU implementations. This problem, as I noted earlier, is primarily a data access problem, external memory access problem. So the GPUs have much higher bandwidth. In spite of the much higher bandwidth, we can still get higher performance on the FPGAs by effectively configuring the FPGA device for the particular data flow and the particular memory scheduling that I proposed earlier. So I want to kind of summarize here why we are getting the speed up, what kind of opportunity FPGA is offering for us here. So when we use the FPGA accelerator that we designed here for this classic problem, a critical problem in using data centers and cloud platforms from a privacy preserving and secure computations perspective, we have provided data flow optimizations as well as conflict-free scheduling. Some of these ideas could be carried over to CPUs and GPUs. For example, the data flow can also be optimization, can also be performed on CPUs and GPUs. But the specific idea here is that we are providing these parallel pipelines. These parallel pipelines are customized for the particular security parameters you have. And then we also have the data mapping onto the on-chip resources we have. We provide this conflict-free scheduling, which ensures that the bandwidth is effectively used between the processors and the on-chip static RAMs you have on these devices. So let me now conclude this talk. Before I do that, there is a significant body of work in the last few years in terms of graph machine learning, going from CNN models to GNN models. This is a very important area of research. We do have a number of publications in this space. In fact, we are developing hardware, software, co-design methodology for FPGAs to do this graph neural network acceleration. I encourage you to visit my website. You can find those details. We look at the graph neural networks, graph convolutional networks, also temporal graph neural networks, in which these graph neural networks have timestamps. The edges are, for example, have timestamps. Edges are changing. The labels are changing. There are a number of interesting problems. Real-life problems can be modeled by using this, and FPGAs play an important role in terms of accelerating those kinds of computations. So let me conclude my talk before we go into some questions by kind of looking at the future, what kind of opportunities are there. I talked about processors, FPGAs, and GPUs. It turns out that some of the vendors, for example, AMD Xilinx, provides this completely integrated single chip solution, which is a heterogeneous chip. You have processors, real-time processors, FPGAs, programmable logic, as well as RISC-enabled, RISC-based vector processors, like data parallel operations you can do. And a number of these RISC processors are combined into a parallel pipeline, parallel array processor, RISC array processor that is available on these devices. They call them intelligent engines. So these devices are currently available. There are software tools available. I've just shown here the performance number, the kind of bandwidth, the kind of parallelism that is available on these devices. This is a single device, a single chip that provides extremely high performance, heterogeneous computing capabilities in terms of general purpose processing, multi-cores, programmable devices, logic, that is FPGAs, as well as on-chip memory, static RAM, plus a programmable array of processors, which is the data parallel engine, all integrated onto a single chip. In fact, the node architectures are evolving in the data centers. These architectures are becoming heterogeneous in terms of processors, GPUs, multiple sockets, multiple types of accelerators, various kinds of memory technologies. I'm just showing here the kind of bandwidth, the kind of performance we can expect on these devices. So this is a very exciting area here in terms of looking at these kinds of devices, looking at these kinds of node level architectures and mapping applications. And finally, also mapping the applications across multiple nodes in such an architecture, which is kind of becoming like the accepted way of accelerating computing on the cloud platforms. So one of the challenges here is programming these kinds of heterogeneous architectures that consists of various types of compute units, traditional multi-cores, like thread level programming or task level programming on this, or on GPUs, for example, CUDA or OpenCL kind of programming, or looking at the FPGAs where you might use high level synthesis or various hardware oriented languages, for example. So I think there is some challenges. There are also some opportunities here. For example, some newer programming models are emerging here, which provides a uniform interface to the various hardware resources. For the various hardware resources, task-based programming or data parallel programming or fine-grained programming on the FPGAs that you want to do. So there are, I'm just giving an example here. This is one API is a parallel programming framework, which is proposed by Intel and various vendors. It's one of the evolving industry standards here, which is used to program this node level as well as distributed architectures in the data centers. So one of the opportunity here for us, which is also challenging in the sense that one needs to understand how this heterogeneity can be effectively used here to get high performance in these implementations. So let me conclude my talk with some remarks here. FPGA technologies have evolved over the last 25 years. These technologies are very, very powerful. They have a similar integration as what happens in the case of state-of-the-art processors or GPUs in the market. They provide various memory technologies, interconnect technologies that are programmable on the device, which is a very important feature that can be exploited. Coherent memory is becoming popular. You can share the data between the processors in a data center, across the various sockets you have, various accelerators, various GPU accelerators. That makes it very fast, very high performance. Implementations can be obtained. I mentioned about an example device in the market, very high performance heterogeneous device in the market, which provides various kinds of parallel computing capabilities on a single chip. So there is quite a lot of debate, discussion as to how this technology can be effectively used. One of the important opportunities here is that if you're looking at low latency applications where latency is perhaps more important than batch-oriented processing, for which GPUs are very, very good. So there are opportunities here in terms of using FPGAs for such low latency applications. So I would like to thank my team and also my sponsors over the years. With this, let me stop here. I've also listed here the various websites if you are further interested. I'm also open for any questions you may have at this time.